Okay, I have a link here. This is a new link. Let me copy this to my note. I hope my microphone is working. Is it working? Yeah, I think it's working. So we have this page. Then I understood what was wrong. Okay, here we can expand this spatial coordinate in terms of material coordinate, a little bit shift in material coordinate. Then this is like I would say like perturbation. So this says like the second order quantity render the third term negligible. So this quantity, because this is a multiple of small things, so this will render this negligible. Yeah. So the smallest remaining term is this. Okay. And then it's called a simple material. But in some case, we have to, we are not permitted to assume that third term negligible. Okay. If sometimes this term we cannot neglect. Yeah. Then we have to we may have to include second term derivative. That's this is a second term derivative. Second derivative. I'm sorry, it's not second term. Second derivative. Okay, in the theories. So I think it is clear. Then we go to set strain tensors. The lengths of the element before and after deformation are given by this. Before deformation, we have this. So after deformation, we have this. Interesting. It's very interesting. The strain tensor E alpha beta and E small e ij are measure of the change in length. Strain tensor is a measure of length. So you can see here you have this, and here you have this. So this one, strain tensor. Why I don't know why there is a 2, but strain tensor is defined to be this. From here, it's straightforward, I think. So then if you use small xi, small xj, you use small eij, and the definition is like this. So this is called strain tensor. The strain tensor large E is called a Green's strain, and small e is called Almancy strain. The names Lagrange strain and Cauchy strain are also used, respectively. Green strain, Lagrange strain. It's complicated. Green strain or Lagrange strain, or Almancy strain, or Cauchy strain. That's small e. This is small eij, right? Is that right? Large eij. This is large e is Green strain and Lagrange strain. Anyway, for these, it is easy to see that both of these strains are symmetric tensors. I don't know if it is easy. I would skip the check whether it is symmetric or not symmetric. See, the point is G symmetric? That's a question. We have done G. G is symmetric, right? See, you can see G. Is it symmetric? I think it's symmetric. So you can change. This is just this is same as like this alpha beta partial beta xi partial alpha xi. So you can change which is G beta alpha. So G, large G or small g, these are symmetric. Yeah, that's why E, strain tensor, is also symmetric. A relation between these two strain measures it's called strain measures, strain tensor. They call the strain tensor by strain measure. Okay, these two strain tensors can be established as which have the matrix form by use of this. This goes so fast, I think. dx. See, I think you have to memorize a lot to understand. See, one thing, you can use this one, right? G alpha G dx. See? Maybe I should work out in my notebook. I think I have to work out in my notebook. That is easier. So, okay, wait a second.